Hello and welcome to another Phi Guy Francois production. Today we're going to be covering regular linear motion problems. And I say regular because this is just the standard form. There's two other types that you could potentially see, which are just derivatives off of this, small things you have to do extra. But let's get down to business. So, a couple criteria for the use of these equations. These equations only work so long as they have constant acceleration and that they are taking place over time. Okay. Now, the reason for this is that these equations could become much more expansive if we held it so that acceleration could change. But in the interests of simplicity and just getting across the basic idea of what's going on, we hold our accelerations constant. Something else that you'll need is you need to have a single frame of reference, which what I mean by that is a way of measuring everything from a single point of view. So this is most often a stationary point on the surface of the Earth for most of our problems, although it could be much more expansive than that, to be a spatial body or a relative universal point in space if we're doing some body work for this. And the last thing that these equations apply to is that these are equations for a single object. Now, when I say a single object, you can refer to a group of objects as a single object if it works out better for you. The problems that we're going to go through are really just about actual single objects, though you could group things into a group of them, and these equations would still apply. So let's get on to the example problem. So first thing, here's our example problem. A 2-kilogram baseball falls to the earth and impacts it with a speed of 25 meters per second. If it started from rest, how high up was it dropped? So let's run through some of the more important parts of this. We have our little handy dandy chart that you can see here. This is how we organize our data. The first important piece that's noticeable is most of the time if you look for data values, if you look for numerical values that are mentioned, most of the time they are actually useful. So this 25 meters per second, definitely actually useful. And the meters per second tells us that this is actually a speed. Now we have to figure out which type of speed it is, so you have to use context. We see the impacts here, so that tells us that it's at the end of something. So we would assign this into the value of being a final velocity. Now, as just a standard rule, of course, though of course you can change it, say that upwards is the positive direction and downwards is the negative direction. So if you want to change that, if you want to say downwards is positive, that's perfectly fine. But again, it all goes back to that frame of reference. You have to choose one way to be positive, one way to be negative. So we have that. The next thing that I noticed from our problem is we can see that it starts from rest. Now, this starting from rest means that it has a zero amount for a speed or velocity either at the beginning or at the end. We've already filled in the end, so of course, beyond the fact that it says that it started at it, we are going to have our initial velocity be 0. The last thing that's actually useful to this is that we are actually on the Earth. So that means that a falling object, if we discount the effects of air resistance, which we are, then we will end up having an acceleration of 9.8 meters per second squared. Now, you may be questioning, well, what about that 2 kilogram? Well, the 2 kilogram isn't actually useful to us because mass does not actually play a part in motion. It will play a part in forces, and it could affect motion, but it does not play a part in the motion calculation. So, the last thing that we want to identify, okay, other than the values that we know, is the value that we want to know. And that value that we would want to know is this delta x value. That's what we're trying to find because we want to know how high up was it dropped from. Okay, so now that we know what we want to know and we have the values that we do know, we have to pick an equation to use because we actually have a good couple of them. Here are the 5 that we know of that we could possibly use, and the ones that we want to choose, we would want to choose based off of the values that we know and the value that we want to know. So that would be delta x, vi, vf, and a. So if we look back at our equations here, the one that makes sense for us to use would be this equation here because it has all of those variables, the variables that we know, a, vi, and vf, and it has the variable that we want to know, which would be delta x. Remember that choosing your equation does not, and I cannot stress this enough, does not have to be about what is on the left side of that equal sign. It is all about the variables that are there and the variable that you want to know. Okay? So we choose this one based upon the because we know the values are given and there is only one variable that we do not know, and that's the one that we want to know. So we have to take this equation and, of course, rearrange it. So we start off with our equation here, and, well, how do we rearrange this? Well, the thing that we rearrange it with, and I refer to this as reverse PEMDAS. So you see PEMDAS right here. We've got our usual parentheses, exponents, multiply, divide, add, subtract. Well, that's when you're simplifying something. You go down this list. When you are solving for something, you go up it, and you use the exact opposite operation in order to find this out. So what I mean by this is we start on the addition subtraction step, and so we look over here and we see, oh, okay, so that thing that we want to find, that delta x, that's attached to something by addition, so we want to get rid of that, so we have to subtract that to the other side. So we end up with this right here. Then what we would want to do is we got rid of anything that's added or subtracted, so we want to get rid of anything that's multiplying or dividing by it. So if we go over here, we see that 2a is multiplying by delta x. The opposite of multiplication is division, so we divide both sides by 2a to get rid of it, and then we end up with this equation, which is now solved for delta x. Once we have done this, it's best to plug in your values at this point. And so we plug in our values 25, 0, and negative 9.8. And this should actually be a negative there. These are switched on top, unfortunately. I accidentally switched them around. But you still understand. We have this equation. Oh no, they're actually in the right order. So we end up with this equation, and let's see what we get out. Well, when we plug this into our calculator, which, don't forget, that top part there should really be in parentheses, because anytime you have a weird thing in a fraction, and by weird thing I mean anything more than a single value, you want to put it in parentheses before you plug into your calculator, otherwise you will end up possibly with the wrong answer. But when we plug it in, we get an answer. Now, negative may seem like it does not make sense, but, and that's a good thing to think about, but it does make sense. Because remember, which way did the ball fall? It fell down, and we said that down is negative direction. So our answer makes sense, and what it means is it was dropped from 31.98 meters up. You can see similar problems for this in your problem sets, but everything goes around this same basic step-by-step formula, which is, first off, list everything that you know as far as the motion variables for the equation. Secondly, identify the thing that you want to know. Thirdly, choose your equation, choose wisely, the one that you want to use, which would be the equation that has all the variables that you know and the one that you want to know. Fourth step, rearrange the equation. Fifth step, plug it in, and then you're done. That's it. Well, we're out of time for this one. I don't want to make it longer than 10 minutes on you, so let's stop it here. You can try the next problem in the next video, and I'll see you in class. Have a good one.